Okay, so we'll start with the last lesson of this uh, book. Okay, that is nuclei or nuclear physics. In simple words, it is nuclear physics. Now we already know that the fundamental particles. What are fundamental particles?
Electrons, protons, neutrons.
Electrons, protons, and neutrons. They are fundamental particles. Okay, so we will start directly from small definitions. The small definitions like what is atomic number, then what is atomic mass, then we will go for IAMU, 1 AMU, atomic mass unit and all. Then we will go for relative abundance. Okay, in that way we can go ahead. Okay, so what is atomic number? Atomic number is represented by Z. Number of protons. Number of protons present in the nucleus. Okay, number of protons present in the nucleus is known as atomic number. So example, let's suppose if you are taking carbon C612, then here atomic number equal to 6. Next is atomic mass. Atomic mass or mass number. Atomic mass or mass number. Okay, that is A. Okay, so it is what? Number of protons and neutrons. Number of protons and neutrons present in the nucleus. Number of protons and neutrons present in the nucleus is known as mass number or atomic mass. So here, if we write C612 again, so atomic mass is equal to 12. So when we write any represent like this, any element, X is the symbol of the element, A is the atomic mass, and Z is the atom ZA. I'll write like this. You can write like this also. So Z is atomic number. Z is atomic number, and then A is atomic mass. Okay, A is atomic mass. So this is how it is given. Now we will discuss this. Already you studied in your grade 11 chemistry. Now we have AMU, 1 atomic mass unit. It is defined as 1/12 the mass of C612. Okay, 1 U or 1 AMU. Okay, atomic mass unit. Atomic mass unit. Okay. atomic mass unit. It is defined as 1/12 mass of C612. 1/12 the mass of C612. That is known as 1 atomic mass unit. Then 1 atomic mass unit is equal to 1 U is equal to what? 1 U is equal to mass of 1 C612. Mass of 1 C612 atom divided by 12. Means we are dividing 1 atom by 12. So then we will get the 1 atomic mass unit. So how do we calculate this one? See, if I am taking 12 grams of carbon, 12 grams of C612, how many atoms will be there here?
6.022 into 10 raised to 23.
Very good. We have 6. Okay, so I can write like this. So that means 6.022 into 10 to the power of 23 atoms will be there in 12 grams of C612, right? 12 grams of C612. Then 1 atom mass is how much? Is it not? What is the mass of 1 atom? So what you will do? You will multiply this with this one divided by this one to get the value. Is it not? Yeah. We cross multiply that to calculate the mass. See, this many atoms will have this much mass, 12 mass. 12 grams will have Avogadro number of atoms. So 1 atom will have how much mass? So we cross multiply it. So what is the value now? So 1.9926. So the mass of 1 atom is 1.9926 into 10 to the power of divided by 2 into 10 to the power of minus 26. 10 to the power of minus 26. Then you'll get 1 atomic mass unit. That is 1.66. 1.66 0539 into 10 to the power of minus 27. This is the value of 1 atomic mass unit. Is that clear?
Yes, sir.
Okay. Can you please copy this? Can you quickly we'll move ahead? See, atomic number means number of protons present in the nucleus. Atomic mass means number of protons and neutrons present in the nucleus. So when we write the symbol here, this is atomic number and this is atomic mass. Next is 1U or 1 atomic mass unit. It is defined as 1/12 the mass of 1/12 the mass of C612 atom. Okay, C612 atom. So 1U is equal to mass of 1 C612 atom divided by 12. Means we have to find out the mass of 1 atom of C612. See, in Avogadro, if you take 12 grams of C612, we get Avogadro number of atoms. And 1 atom mass is how much we don't know. We have to cross multiply that. How? 1 into 12 divided by 6.02. If you do it, you'll get this answer. Then once you're done with that, divide by 12, then we'll get the 1 atomic mass unit value. That is approximately equal to the mass of proton. Clear? So can I go ahead now?
Yes, sir.
Yeah, okay. So now here we have relative abundance. Like suppose we are taking one example of relative abundance and isotope. Okay, before that I'll start with isotope. What are isotopes? What are isotopes?
Same atomic number, different atomic mass.
Yeah, atoms with same atomic number, but different atomic mass. Same atomic number but different atomic mass. So example for this is what? C612, C613 and C614. Okay, same atomic number but different atomic mass. Next is isobars. What are isobars? Atoms with
opposite, no?
Atoms of atoms with same mass number, but different elements. Yeah, but different atoms or different elements. Okay, of different elements. Example is what here? Isobars N714, C614. Atomic mass is same. Then what are isotones? Isotones means atoms with same number of neutrons. Atoms with same number of neutrons is said to be isotones. What are the example for this? The example for this is like C613 and 714, oxygen 815. So 13 minus 6 is 7. 14 minus 7 is 7. 15 minus 8 is 7. So this is the value. Is that clear? So once again, isotopes is atom with same atomic number but different atomic mass. Okay, so example is C612, C613 and C614. Isobars means atom with same mass number but of different elements. N714 and C614. Isotones, atoms with same number of neutrons, that is C612, N714 and oxygen 815. Just to take the difference, we'll get the number of neutrons. Now I'm going to discuss about the chlorine isotopes. So here we have one more example like chlorine. So when we see chlorine is how much? 1735 and 1737, right? Do you know this? There are two isotopes of chlorine. See here.
Yes, sir.
Chlorine, we have 1735 and 1737. But when they are writing in the periodic classification table, do they write like to both the isotopes? They don't write, is it no? They don't write both the isotopes. Only one value is there. What is the atomic mass of chlorine in periodic classification table?
35.5.
35.5. Very good. 35.5. That is the value given in the periodic classification table. Now, according to the atomic mass unit, okay. So 34.98. So chlorine has one is 35.98 U and the second one is 36.98. 36.98 U. But if you are taking 1 kg of chlorine, if you are taking 1 kg of chlorine, how much of that will be that is 35.98 and how much will be 36.98? Okay.
75% will be
Around
35.
30, yeah, around 75.4%. Okay. This is around 75.4% is this much, and the remaining is 24.6% is this much. Means if you are taking 1 kg, 1 kg of chlorine from the nature, okay, from the nature, if you collect it, then this much will be 75.4% will be this isotope, and 24.6% will be the other isotope. So what we are trying to find out? We are trying to find out the relative abundance. Okay. After finding the relative abundance, then we can easily find out the average atomic mass. Okay. So this is a relative abundance and average atomic mass and average atomic mass. Okay. Average atomic mass, relative abundance and average atomic mass. So how do we find out now average atomic mass? Average atomic mass. So just multiply it. It is equal to how much? 35.98 into 75.4 plus 36.98 into 24.6 divided by 2. Okay, divided by 100, sorry. So we get this how much? Now the value will be equal to 35.5 U something around. Okay, 35.47 U. 47. So that is the reason why they write this value in the periodic classification table. So this is possible for hydrogen also. If you take hydrogen also, example, one more example I will take. So what is the example? 1H1 is there. These are the isotopes of hydrogen. 1H1, 1H2, and 1H3. These are the isotopes of hydrogen. But when they are writing the isotopes of hydrogen, we don't write 1H, 1.1, 1.2, something like that. Why? Because 99% of hydrogen is this only. This is 99%. This is around 99% or more than that. So that is why no need to write that value, more than 99%. Even in case of if you take carbon C612 and C613 and C614 also, here this is more than 99%. Understood? This is greater than 99%. So that is why we don't have to write 12.1, 12.2. So in the periodic classification table, this is there, and in the periodic classification for hydrogen, it is like this. Understood now? Is that clear?
Yes, sir. Yes, sir.
Yes, sir.
Now, so here next is what we'll discuss about the mass of proton, neutron, and electron in terms of one atomic mass unit. Okay. Now here. So yesterday I have sent the recording, okay, for the 3 derivations also. That is radius of the nth orbit, and velocity of electron in the nth orbit, and energy of the nth orbit. Okay, these 3 derivations are there. These 3 yesterday I have sent it to you, recorded and sent that to you. Okay, so that will be the that will complete the full chapter. Then next, here we have we will discuss about the mass of proton is how much? That is 1.00727 U in terms of atomic mass unit, and that is equal to 1.67 into 10 to the power of, that is 1.67 into 10 to the power of minus 27 kg. Already we know this is the mass of the proton. Then we'll write the mass of the neutron and mass of the electron. So if you see the mass of electron is 0. Mass of electron is 0.00055 U. This is the mass of electron. Now there are 3 names given for this. Okay, what is this? 1H1, 1H2, 1H3. This is known as hydrogen. These are the names. Okay, they can confuse you with the name also. Sometimes they will not give this one. They will only give this value. Hydrogen, deuterium, and tritium. Okay, tritium, hydrogen, deuterium and tritium. Okay, and mass of electron is what? 0.0005 U. Okay, that's the mass of the neutron. Okay, next one. Neutron, that is electron. Next one is for hydrogen. Hydrogen atomic mass is 1.00783. 1.00783 U. And mass of neutron is mass of neutron is, we have 1.00866, 1.866, which is equal to 1.6749 into 10 to the power of minus 27 kg. These are the values of electron, proton, neutron in terms of atomic mass unit, 1 unit. Once again, what is atomic mass unit? Atomic mass unit is that is 1 by 12 of C612 atom divided by 12. Means if you are breaking one atom of C612 into 12 parts, that one part is 1 AU. Okay, that's a standard. Why they have taken, why C612 is taken as a standard value? There is a reason behind it, because it has equal number of protons. The number of protons, neutrons, and electrons are same. Means it has 6 number of electrons, 6 number of protons, 6 number of neutrons. That is a reason it became a standard atom, both in physics and chemistry. Okay. Now, and also if you go to the discovery of discovery of neutron, Chadwick is the one who discovered the neutron, and he got the Nobel Prize in 1935 for the discovery of neutron. Okay. Now, how do we calculate the number of neutrons? See here, A is equal to what? A is equal to Z plus N. So if you want to calculate N equal to A minus Z. Okay. N equal to A minus Z. Is that clear? Next one, size of nucleus. Size of the nucleus. Size of the nucleus. So size of the nucleus, how did they find out the size of the nucleus? You know, alpha scattering experiment. Okay, where did we study this? Alpha scattering experiment. Can anyone say?
Alpha scattering experiment.
Rutherford alpha scattering.
Gold foil. No? Last year we studied in chemistry. This year we studied in atoms.
Yeah, in grade 11 also you studied in chemistry and atomic structure, and now also you studied in atoms chapter. Okay, in atoms chapter also you studied about Rutherford alpha scattering experiment or Rutherford gold foil experiment. Okay, and also this was explained by Giger and Marsden. There was a question last year in boards that is for 3 marker. It is an example question. Okay, second example question of the chapter that came for 3 marker, and all the students thought that it is out of portion because Giger Marsden it was never explained, but it is there because if you study the theory of Rutherford model or alpha scattering experiment, Giger and Marsden have explained this one. But most of them, they thought it is out of portion and they left it. What was that? What was the question there? It was closest approach. That I'll explain now. Okay, let me explain this. Let me first write this formula and then I'll explain that also. Okay, so it says that here we have R is equal to, the formula is R is equal to what? R naught into A to the power of 1 by 3. Okay, R equal to what? R naught into A to the power of 1 by 3. What is R naught? R naught value is 1.2 into 10 to the power of 1.2 into 10 to the power of minus 15 meters. Minus 15 meters. That's the value of R naught. R naught is what? Unit radius. Okay. Radius of that is also known as unit radius. A naught, A unit radius. We studied this in the previous chapter also. A0. It was represented as A0. A0 is 1.2 into 10 to the power of minus 15. Okay. That's the radius of the first orbit. Now, A is what? A is the atomic mass here. A to the power of 1 by 3 is A is atomic mass. So if you want to find out the radius of the nucleus, R is equal to R naught into A to the power of 1 by 3. Just you do it, then you'll get the answer. Then how did they find out actually this value? What is the story behind it? See here, they use the formula. What is that? Density is equal to mass by volume. So the nucleus is like a sphere, small sphere. What is the volume of the sphere? Volume of the sphere is
4 by 3 pi r cube.
Very good. 4 by 3 pi r cube. Very good. 4 by 3 pi r cube. Then what we did after that? We cross multiply that. R cube is equal to how much? R cube is equal to 3m by 4 pi rho. Okay. 3m by 4 pi rho. Then 3m by 4 pi rho. Then we remove that, then we need to find out R value. R value is equal to how much? R is equal to, R is equal to, density is mass by volume. So we got R is equal to how much? R is equal to 3m by 4 pi rho whole to the power of 1 by 3. This is the way they calculated the radius. Is that clear now? So they followed this principle behind it. Now, anyways, we'll go ahead now. That is mass energy and nuclear binding energy. Is this clear, everyone? All of you? Is this clear?
Yes, sir.
Yeah.
Yes, sir. Yes.
So what is density here? Rho is what? Density of the nuclear matter. Density of nuclear matter. So one more thing here. What is, we have nucleons. One more term called nucleons. What are nucleons? Protons and neutrons together. Protons and neutrons together are known as nucleons. Okay, protons and neutrons together are known as nucleons. Okay, next one, mass energy and nuclear binding energy. Next one is mass energy and nuclear binding energy. Mass energy and nuclear binding energy. Mass energy and nuclear binding energy. Okay, so here mass energy. What is mass energy? See what happened is Albert Einstein, he explained, as I told you, 1905. Year 1905 was celebrated as year of physics. And even after 100 years of that 2005 was also year 2005 was also celebrated as a year of physics. After 100 years of the publication of three papers, very famous papers of Albert Einstein. So, you know, there are three papers. The first one is, photoelectric effect. The second one is E is equal to mc square. And third one is, what is that? Brownian motion. Okay, first one is photoelectric effect, E is equal to mc square. Third one is Brownian motion. And in year 1906, he published one more paper, that is special theory of relativity. So, according to Albert Einstein, he says that when any particle, so suppose if any particle is moving with the speed comparable to the speed of light, means what? Like maybe 50% the speed of light or 25% the speed of light. In that situation, you cannot apply Newton's mechanics. Why? The mass is constantly changing, the length is changing, time is changing. We say mass contraction, time dilation, length contraction. That is not there in our syllabus, but that comes under special theory of relativity. So you cannot apply Newton's mechanics. For that, you have to apply Einstein's mechanics. That is also known as special theory of relativity. So according to that, he says that mass can be converted to energy and energy also converted to mass. Okay, this concept is very easy. Like suppose if you burn 1 kg of coal, it can be easily converted to energy. Everyone knows about it. But how will you convert energy into mass? That was a question. That was a thing he thought. Okay, what Albert Einstein thought is, can I convert energy into mass? And he did one experiment also for that. I'll explain that. Okay, so for that he brought a mass energy equivalence relation. Okay, so Albert Einstein's mass energy equivalence relation. Mass energy equivalence relation. What is the formula? So the formula is E is equal to mc square. Okay, E is equal to mc square, where m is the mass and c is the speed of light. Okay, mass can be converted to energy and energy can be converted to mass. 3 into 10 to the power of 8 meter per second. Okay, this is the value. So how do we do that? Okay, I'll just give a simple example. Okay. So I'll give an example here. Example is here. Suppose that is pair production and annihilation. Pair production. See, in pair production, this is not there, but just I would like to explain, because the curiosity is every student will ask, sir, it is very easy to understand mass to energy, but how will you convert energy to mass? That's a question. Pair production, what happens? Suppose this is the energy. So here it is H nu. H nu, what happens? They scatter into electron and positron. Okay, that is how the pair production takes place. Next is annihilation. In annihilation process, what happens? A positron and electron come together. Okay, so what will happen here? An electron and a positron, they come together. E plus and E, they come together, and what happens? That is H nu is formed. Is that clear? Electron and positron, they come together and H nu. That means energy formation takes place in annihilation. So that is how mass is here mass is converted to energy, here energy is converted to mass. Okay, this is a simple experiment to demonstrate this. Next is nuclear binding energy. Is it clear, all of you? Yes, sir. Is it
Yes,
clear?
sir,
About
it's
it?
clear.
Don't sleep, okay? Just it's a very easy chapter, okay? And also it carries, I think, 3 to 4 marks, okay? And very easy lesson. These 3 lessons: dual nature of matter and radiation, dual nature of matter and radiation, and atomic physics and nuclear physics. All together they carry 12 marks, and very easy, okay? It's not that difficult. Maybe a numerical will be asked from each also, okay? Now, here we have nuclear binding energy. So to calculate nuclear binding energy, we need to first do the concept of mass defect. Okay, nuclear binding energy. Are you able to see the board properly, man? All of you?
Yes, sir.
Yes, sir.
Okay. Now, so before doing nuclear binding energy, first we'll discuss about the mass defect. Okay, what is mass defect? Mass defect is denoted by delta M. Okay, mass defect is denoted by a delta M. So mass defect is what? It's a difference. The difference in mass of a nucleus. The difference in mass of the difference in mass of a nucleus, and mass of a nucleus and its constituents, the difference in mass of a nucleus and its constituents is known as mass defect. Okay, so what is the formula here? So delta M, we will first calculate delta M. What is delta M? So delta M equal to Z into MP. Delta M equal to Z into MP. That means number of protons into Z means number of protons into mass of the proton plus number of neutrons. How do we calculate number of neutrons? A minus Z into Mn. Okay, minus atomic mass, minus actual atomic mass. Okay, or we write small capital N. Okay, here the difference between the mass of a nucleus and its constituents. Okay, and its constituent, that is known as mass defect. This is the way we calculate the mass defect. Now, so what is the binding energy now? The energy here. So amount of energy required to separate the nucleons. Okay, binding energy. I'll write the definition here. Binding. Is it clear? See, once again, mass defect is Z into MP, means number of protons into mass of the proton plus number of neutrons into mass of the neutron. That is mass, and minus actual mass. Actual mass is capital M. So it is a difference. Don't take it as like only a subtraction. Sometimes you may get negative also, but we are just writing the difference. Difference means whatever comes first, bigger number should be written first. Now, after that we have binding energy. Okay, that was about the mass defect. Okay.
Sir, less than 1 minute, sir.
Oh, okay.